Electric field lines. Electric field lines are imaginary lines. In reality, this line doesn't exist. Only we can imagine electric field lines, magnetic field lines, and gravitational field lines. They all are imaginary lines. I'm trying to explain through this simple experiment. Here, it's a magnet. Now, I'm putting another magnet near to this one. There is a force on this magnet. We consider it that the magnetic field lines of this magnet exist in this region because when I'm putting this magnet, it experiences the force. It's mean this magnet has magnetic fields over here. So these lines are imaginary lines. We are feeling the effect of this magnet in this region around this magnet. It's so we consider an imaginary lines about this magnet. These lines are imaginary lines. These are magnetic field lines similarly around a charge. These lines are imaginary lines of this positive charge. In reality, these lines doesn't exist. So the direction for positive charges, the direction of lines is outward. For negative, the direction is inward. For positive charges, the lines point outward away from the charges. For negative, the lines point inward towards the charge. Electric field lines separate three-dimensionally. Here, two-dimensional, but they separate like a sphere in all directions around a charge. For example, in magnets, the electric field magnetic lines also here. It experiences a magnetic force. So, the electric field lines separate three-dimensionally like a sphere in all directions. And closer to the charge, the field lines are stronger, and away from the charge, the field lines are weaker. Similarly, in magnetic field, close to the magnet, the field is stronger. But away here, there is a magnetic force, but weaker as compared to here. So closer to the magnet or charge, the field, electric or magnet, is stronger. Away from the charge, the field is weaker. Now, electric field of two opposite charges are dipole. Di mean mono, one di mean two. Dipole means two charges of equal magnitude but having opposite signs, positive, negative, and placed close to each other makes a dipole. Two charges of equal strength but opposite signs are placed close to each other, they form a electric dipole. Electric dipole, the field starts from positive charge and ends at negative. Same here, starts from positive and ends at negative. The number of field lines of the positive charge are equal to the number of field lines leaving the positive charge is equal to the number of field lines entering the negative. Both lines, number of lines are equal for both charges. For two similar charges, for two opposite charges, for two similar, they both are similar. Positive, both are positive. For both positive charges, they both repel each other. They attract each other. Opposite signs attract each other. Similar charges repel each other. And the field lines are considered maybe like this. For opposite charges, field lines are considered, these are imaginary lines. We considered like this. And here they repel each other. They move away from each other. So field lines are like in this shape. they repel or bend, the field lines are weaker. Here the field line is stronger at the middle. The field is stronger between the charges because the forces are add up. Between the charges at this point, the field is stronger because both fields are add up over here. Here the field is weaker because both charges cancel out. Between the charge, the field is weaker between the charges because they cancel out. At a certain point, the field strength is zero or called neutral points. And at the center, the field is almost zero, and this point is known as neutral point. For negative charges, the pattern is same, but the direction of arrow will be opposite. The negative charges direction are same, but arrow is opposite. Some properties of the charges: no intersection means the field lines never intersect each other. Intersect means they never cross each other. For example, one field line is going in this direction and the other in this direction. It's impossible. Why it's impossible? The reason because the electric field is a vector quantity. A vector has only one direction. If they intersect each other, at the point of intersection, they have more than one direction. In this direction and this point has two directions, this one and this one. So it's impossible for a vector quantity having direction more than one. So that's why field lines never intersect each other. The first property. Second, starts from positive charge and ends at the negative charge. Third, the direction. The direction of field line. The direction of field lines for positive is outward, for negative is inward, but at the curve place, the direction of field lines is tangent. Direction is tangent to the field lines at that point. The tangent means this line, blue line is tangent to this point, and this blue line is tangent to this point. Tangent line means the line which touch at a single point and go straight. So at this point the direction is in this direction, and here the direction is in this direction of the electric field. Tangent to these two lines are tangent to this point and this point. So direction is for curve, the direction is tangent to that point. Strength closer to the charge strength is more as compared to the away from the charge. Force. Electric field lines here, electric field lines, they attract each other. That's why they're moving towards each other and field lines become shortened. It's mean there is a force of attraction, and here the force is repulsion between the opposite. The electric field lines tend to shorten, which explains why opposite charges attract. That's all about field lines.